Classifying differential equations is going to be an ongoing trial for us throughout this course. Being able to look at a differential equation and saying what type it is really going to help us figure out what method we want to use to solve it. Now, since we're talking about differential equations, remember all a differential equation is an equation that has a derivative in it. And we saw plenty of these throughout Calc 1, Calc 2, whatever calculus you had. Something as simple as y prime is equal to 2x. That's a differential equation. Now, to solve this differential equation, we'd want to figure out what y was equal to. Now, of course, this is a pretty simple problem, but you want to think about it more in depth than what we had before. You want to think about this in terms maybe differential form, maybe a little bit easier to see. You need to distinguish the difference between independent variables and dependent variables. Since this is a derivative of y with respect to x, y is the dependent variable, x is the independent variable because that's what's changing. We're looking at changing y as x changes here. So to solve something like this, of course, we're going to have to integrate, which is going to be a running theme throughout this entire semester. So now that we know a differential equation is just an equation with a derivative, how do we classify it? Well, the first one is we're going to classify it as type, or what type of differential equation is. The good news here is the name of this particular course is ordinary differential equations. So the answer to this question for us all semester is going to be ordinary. But the two types that you generally see are ordinary and partial. Now, ordinary differential equations are equations where the derivatives are ordinary derivatives, kind of like what I just put up there a second ago. dy dx is equal to 2x. That's just a regular old Calc 1 derivative. If it's a partial differential equation, that means you have partial derivatives. The partial of y with respect to x is equal to 2x. Now, the idea here, for those of you that may not have had like a Calc 3 level class, when you're taking a partial derivative, that means that y could be a function of more than one variable. In the past, we'd see y as some function of x, but there's no reason to assume that y couldn't have other independent variables and say y is a function of x and z. So how do we take a derivative when there's more than one independent variable? We do that by using something called the partial derivative, which we'll take a little bit more look at that in just a little bit. But the easiest way to visually see it, if you see a derivative that has the regular d symbol, that's an ordinary derivative, so an ordinary differential equation. If you see one that has this kind of 2 looking thing that I have written here, it's actually a Greek symbol that, if you take a look at your textbook, looks something like that. That's to denote that it is a partial derivative. Now, there's an entire course and courses on how to solve partial differential equations. Incredibly useful, but for this course, we're generally going to look at ordinary differential equations. So the answer to what type it is almost going to be always ordinary. Then we're going to talk about what order it is. The order of the differential equation is really just the highest derivative. So a first order differential equation is one where the highest derivative would be like y prime. A second order would be, well, a little bit harder looking, but you see the highest derivative present is a second derivative, so this would be a second order differential equation. Well, very, very simple for that one. The last basic classification we're going to look at is linear. Now, this is where really understanding the difference between an independent variable and dependent variable is going to come into play. A linear differential equation means that all the dependent variables and its derivative are raised to the first power and no dependent variables times its derivatives. All right, kind of scary. So it's going to mean that all the independence variables and its derivatives are only raised to the first power, and there are no dependent variables times its derivatives. So basically, most of the time, y is our dependent variable, x is our independent variable. So one way to read this is all the y's and all the derivatives of y's have to be raised to the first power, no y stuff multiplied together. So let's classify here real quick. Using just these three basic ones. We're going to add a bunch of stuff to this as we move along. If we take a look at, let's say if I said 2y double prime minus 6x is equal to 0. All right, if we had to classify this, well, since I'm using the prime notation, that means that this is an ordinary differential equation. So our first classification of type, ordinary. The order, since this is the second derivative, this would be a second order. Now, is this linear or nonlinear? Well, in this case, I'm only looking at the dependent variable, which is y's. All y's and its derivatives are only raised to the first power, and we don't have any y stuff, any y stuff multiplied together, so this is linear. What if I had x squared y triple prime plus 2xy equals 0. Again, pretty much always, like I said in this course, this is ordinary. Since the highest derivative I see here is this triple prime, this would be a third order. And is it linear? Well, I don't have any y's raised to powers or any y's times y stuff, so this is also linear. Let's do one more here. What if I said y double prime plus 3xy y prime is equal to 0? Again, ordinary differential equation. Again, for it to be a partial, you'd have to see this weird partial symbol like this, something like that, for it to be a partial. So this is an ordinary differential equation. Highest derivative I see is 2, so this is a second order. And well, right here I have y times y stuff, which means this is nonlinear. Okay, so classification, most of the time we're going to use order and linearity a lot this semester. Ordinary just kind of gets thrown in there just to kind of remind us that we are taking an ordinary differential equation. So let's take a look at just a little bit of notation here, and this is where this gets a little bit scary. Let's take a look at, and then look at it spelled right. Generic, by the way, ODE, you'll see this a lot, is just ordinary differential equation, right? Again, ordinary means that no partial derivatives. We can write it like this. Let's assume that y is our dependent variable. We can write an nth order differential equation like that. That's an nth order derivative. If you can always isolate that alone if it's linear, then we can end up with on this side some function that involves x's, y's, the derivatives, y double prime, all the way up to the n-1 derivative of that. So what does this mean? If this is an nth order differential equation, then you can have the independent variable, which in this case is x. You can have any functions of x, y's, y prime, so on and so forth, all the way up to the one less derivative than what we have here. So this is an nth order differential equation. All right, so that's our generic form that we're going to write a differential equation. When we just want to talk about any generic differential equation, we're generally going to write it like this. Now, as we've seen in the past, we don't always get a unique solution when we're solving a differential equation. Let's go back to Calc 1 and look at the very first differential equation I wrote on the board today. Something like this. Now, if I ask you to figure out what y is, you'd actually have to do, we're going to do this slightly differently in our next lecture, but here's one way to think about it. To figure out what y is, I need to integrate, and we need to integrate both sides. And remember, whatever you do to one side, you got to do the exact same thing to the other side. So if I integrate this side with respect to x, I'd have to integrate this side with respect to x also. So here you can kind of see that the dx is reduced and I get the integral of dy. And of course the integral of that is just x squared plus a constant. The integral of y is just, or dy is just y. Okay, so this would be our solution. The problem is, that's not a unique solution, because remember, c is any constant. What we ended up with here is an entire family of solutions. What those all are, those are all parabolas shifted either up or down. So something like this, who knows, something like this. So this would be like if c is 0, c is 1, c is 2, or you can even have it shifted down. So what you end up with is this entire frame. Now remember, this is a continuum here. I just drew a few in there. We have an infinite number of solutions depending on what c is. Now, basically what's generally going to happen, if we have a first order differential equation, we have what's called a one parameter, because we only have one letter we don't know, one parameter family of solutions, called the whole group a family. If it was a second order differential equations, well, when we think about it, you'd have to integrate twice, so you'd have two integration constants. So that would be a two parameter family of solutions, so on and so forth. So to figure out what these arbitrary constants are and narrow down what solutions we'd be looking for, we have to know something about the function itself. And more specifically, the higher order the derivative in the equation, the more information we need to know about what's going on to pin down a single solution. So let's talk about conditions. Something called initial conditions. Most of the differential equations that we deal with this semester, when we're going to find a specific solution, we're going to be using initial conditions. Initial conditions just means that we know something about the function all the way up to the n-1 derivatives at a specific point. So let's say this is our nth order differential equation. So to find all the arbitrary constants for an nth order differential equation, you need n initial conditions. Okay, so if you're solving an nth order differential equations and you want to find a specific solution, not just an arbitrary solution, a very specific solution, then you're going to need n initial conditions. So the way that this is represented, again, the notation looks scary, but when you actually see them in your work, it's not that intimidating. Let's see. So I'm going to start with here. This is our same nth order differential equation. Some function of x, y, y prime, all the way up to the n-1 derivative. Well, you're going to need your initial conditions. This would be y at, excuse me, let's say x naught. Now, most of the time for a lot of textbooks, and even some will say that this has to be at 0, but it doesn't. It can actually be at any same spot. We know what that is. We also know y prime at x naught. That's, I don't care how you do it, that's y1, who knows, y double prime at x naught. Notice that we know something about all of these, all the way up to the n-1 derivative evaluated there. So notice, we end up with n things here that we know about. Now, to be an initial condition, it's always at the same value that we know it at. So let's try one very, very quick example here. So you can kind of see what I mean by this. There's a lot of weird symbols going up. You know, I said, find the, let's just say, find the exact solution. Let's do a real easy one. Let's do y double prime is equal to, let's do the same thing, 2x. Let's say that we know y of 0 is 4 and y prime of 0 is 5. Now notice here, this is a second order differential equation. I know something about the function all the way up to the n-1 derivative. So since the highest order here is 2, I know up to the first derivative. So again, we're just going to kind of do this simply. We would integrate both sides. I'm just kind of going to wave my hands here a little bit because we haven't really got to our method yet. I'm going to integrate both sides with respect to dx. Of course, if we integrate the second derivative, you're going to get the first derivative. That's x squared plus c. Now notice, I know something about this, right? I know that y prime at 0 is equal to 5, which means y prime of 0 would be 0 squared plus c has to be equal to 5, which means c has to be 5. So now I know something. I know y prime is equal to x squared plus 5. Now I'd have to integrate again. All right, so I'm just going to move it up here. So if we integrate y prime, again, just kind of being lazy with this notation, we'll get to more precise notation in next lecture. If you integrate the derivative, of course, you're just going to get y is equal to 1/3 x cubed plus 5x. Well, we know something about this function. Again, I know y of 0 is equal to 4. So y of 0 is 1/3 0 cubed, oh, I forgot my c, plus 5 times 0 plus c. And we know that that has to be equal to 4, or c is equal to 4. So the exact solution to this differential equation, y is equal to 1/3 x cubed plus 5x plus 4. So notice for our second order differential equation, we needed 2 pieces of information to figure out what all the constants were. Now, if we hadn't done that, we would have ended up, don't write this down if you're copying it. If I didn't have these 2 initial conditions, basically the 5 and the 4 would have just been replaced with arbitrary constants. We would have ended up with 1/3 x cubed plus, some c1x plus c2, just 2 different constants.